So what about apparent power? Power isn't of just one form. We have real power. In this case, we have power being delivered from a generator to a load. If we look at the waveforms for this little circuit here, we have the voltage shown in red and the current shown in blue, and the product of those two gives us the power in green. We can see for this particular set of waveforms, that green waveform is always on the positive side. That means power is always being delivered from the generator to the load. And this is what we call real power. In the second example, we have an inductor in our circuit. And in this case, we can see the voltage and the current are 90 degrees out of phase with each other. If we multiply that red and blue waveform together, our green waveform now is sometimes positive and sometimes negative. This represents power flow going to and from generator and load and back again. In this case, the net power transfer is zero because it's oscillating with time. Similarly, if we have a capacitor in our circuit, we have the same scenario, only this time the voltage and current lag each other, and so the net power is also oscillating with time, but it is 180 degrees out of phase with respect to the previous example. So active or real power, this is the power that does work. This is the power that transfers energy from one form to another. This is the power that as a consumer we pay for. And reactive power, this is the power that flows between capacitors and inductors. Consumers do not pay for this power. It is measured with a unit called VAR, or volt amps reactive, or the kilovar or megavar for larger denominations. So what about apparent power? Well, in the real world, our loads look a little bit more like this. They're a combination of resistors, inductors, and capacitors. Let's draw the waveforms for these. First, we can plot the real power. That's the green component here, and we can see that it lies entirely along the x-axis because all of this power is real. It's power we pay for. Now let's draw the magnitude of the reactive power through the inductor. This component has positive VARs, which we've drawn in the y-axis. We've also got a reactive power through the capacitor, but remember from earlier, the power through a capacitor is 180 degrees out of phase with that through the inductor, and so they cancel out. The net reactive power in this case, shown in purple, is a small positive quantity. So the apparent power is simply the vector sum of all of these different components, which we can denote with this little orange arrow here. We can use Pythagoras' rule to describe an equation. We could say that S is simply the square root of the real power squared plus the net imaginary power squared. This also leads us to one other concept, the power factor. We can describe the angle between the apparent power and the x-axis, which represents a real power, as an angle phi, and if we take cosine of that angle, it gives us the ratio of the real power to the total apparent power. This is what we call the power factor.